On October 30th, 3I-Atlas was supposed to reach its closest point to the sun and then slowly fade. That was the plan. That's what scientists expected.
That's what happens with every comet.
But 3I didn't follow the plan. Instead, it exploded in brightness, faster and more intensely than almost any other comet at a comparable distance. And nobody knows why. Even stranger, the brightening doesn't follow any known pattern. What's happening to this interstellar visitor right now doesn't fit our models. And that makes it the most fascinating object in the solar system. Since October 30th, telescopes across the world and beyond have been observing something unprecedented. 3I-Atlas passed its perihelion 117 million kilometers from the sun. That's roughly the distance between the sun and Venus. At this distance, a comet should become active, yes, but controlled, predictable. But 3I? Its brightness increase exceeds that of most Oort cloud comets at similar distances by several magnitudes. Dr. Mikkel Bannister, who's been tracking the object for months, called it unprecedentedly puzzling in an interview. But here's where it gets interesting. The Mars orbiters, which had a perfect viewing angle while 3I was hidden behind the sun from our perspective, documented something unusual. Jets, massive fountains of gas and dust shooting asymmetrically from the surface. Not evenly, not predictably, but pulsing. As if the comet was reacting. One researcher described it this way: water is shooting out like a fire hose running at full blast. But here's the problem. At the measured distance from the sun, this shouldn't be happening. Not at this intensity. So what's driving 3I? On August 6th, even before 3I reached its perihelion, the James Webb Space Telescope pointed its NR-SPEC instrument at the comet. Infrared spectroscopy, the method by which we read the chemical composition of objects in space. And what Webb found was extraordinary. Researchers identified molecules that had never been seen in these concentrations in a comet before. High amounts of carbon dioxide, we already knew that. But also carbon monoxide, methanol, hydrogen cyanide. These aren't just frozen gases. These are prebiotic molecules, the chemical building blocks that, under the right conditions, can lead to life. And then came the second surprise. The spectroscopic data showed something researchers described as unusually high nickel abundance. Nickel, a metal that's extremely rare in comets from our solar system. But in 3I, it dominates the spectrum. This confirms what we already suspected. 3I comes from a molecular cloud with completely different chemistry than the one that formed our solar system. It's a relic, a snapshot from a time over 7 billion years ago when its home star was just being born. And this chemistry is the key to everything, because now, as the sun melts away its frozen layers, we're seeing for the first time what an interstellar object is really made of. Not theory, not models, real data. And it doesn't match what we expected. But the chemistry is only part of the story. The other mystery is how 3I is moving. The asymmetric jets, those fountains of gas and dust, are creating tiny but measurable thrust forces. This is called the non-gravitational effect. In normal comets, it's minimal.
But in 3I,
it's accelerating the comet, changing its orbit, making it spin. Researchers have tried to create a rotation model, but the data doesn't make sense. The jets don't fire continuously, they pulse, sometimes active for hours, then suddenly silent. One theory, the comet has an extremely irregular shape, and when certain regions face the sun, they explosively vaporize. Sounds logical, but then researchers noticed something. The jets sometimes fire from the wrong side, from areas that should be in shadow. That means either the surface stores heat in a way we don't understand, or there are internal chemical reactions happening independently of solar heating. Both raise questions we can't answer unless 3I returns. And that, it won't. On November 2nd, the last observatory lost track of 3I. It's now too faint, too far, too fast. The Mars orbiters, our last hope to observe it after perihelion, have lost sight of it. That means whatever happens to 3I in the coming weeks, we won't see it. And when it reappears in Earth's morning sky in early December, it will be so faint that only the largest telescopes will be able to detect it at all. We missed our window. And the next interstellar object could be years away. So what have we learned? We now know interstellar comets aren't just different comets. They're fundamentally distinct. Their chemistry, their behavior, their structure, Everything points to the conditions under which they formed being completely different from those in our solar system. And that is what's fascinating. 3I is a messenger. It carries information about a gas cloud that collapsed billions of years ago and formed a star we'll never see. It shows us that the building blocks of life aren't unique. They're drifting through the galaxy, frozen, preserved, waiting. And maybe life on Earth wasn't born here. Maybe it arrived exactly this way. In a comet from another star 4 billion years ago. 3I-Atlas is now on its way out, accelerating, fading. In a few years, it will have left our solar system. And in a few million years, it will arrive somewhere else. But us? We've received the message. We now know we're not alone in this galaxy, not because there's life out there, but because the ingredients for life are everywhere. And the next visitor, maybe it's already on its way,